Let's explore how the Markov property influences the relationships between regular conditional distributions of our process at different times. Start with a filtered probability space and an adapted process which satisfies the Markov property. Now let's suppose that the state space for this process is a regular Borel space so that we can be assured that for any pair of random variables xs and xt in the process, a regular conditional distribution exists. Let's call this probability kernel QST. That is, it's defined by the conditional expectation of f at xt given xs is equal to the integral of the function f against the probability kernel q of st at xs and dy. In other words, this is capital Q st of f evaluated at xs. Now this statement didn't involve the Markov property at all. The Markov property will tell us something about how QST relate to each other for different values of s and t. To see how that goes, let's take 3 times r less than s less than t in our time set. Then if we integrate f against the regular conditional distribution at times r and t, evaluated xr, well, what we just saw was that that's the same thing as conditioning f at xt on xr. Now we'd like to insert s in the middle, since s is in the middle between r and t. And so we note that since the sigma field generated by xr is contained in the sigma field up to time r, because x is an adapted process, and that's contained in the sigma field up to time s, because we have a filtration, I can then use the Tower property and condition on the inside on the sigma field fs. But this inside conditioning is given by applying the transition kernel at times s and t. But now, since this, q of st at f, is another bounded function, this conditioning of a function of xs on xr is given by the kernel at times r and s. So that says that at least on the random variable xr, applying the transition kernel qrt is the same as applying qrs after qst. Let's make that a little more precise in terms of the actual probability kernels. If I take the expectation of both sides and apply the change of variables theorem, that means that integrating this function against the law of xr is the same as integrating this function against that law, and that's true for all bounded functions f. Now here what we have is the integral of f against the law of xr product with the probability kernel q of r and t, whereas on this side what we have is the integral of f against the product of the law of xr with q of rs times q of st. And we know that means that these two measures are the same measure. And we also have our uniqueness result that says that since we're dealing with a regular Borel space, which is therefore countably generated, these two measures being equal means that these two probability kernels are equal. So the conclusion is that the collection of all of these probability kernels satisfy the following relationship. The kernel at times r and t can be achieved by taking the kernel at time r and s and integrating out the y variable against the kernel q of s and t. At least that's true almost everywhere with respect to the law of the process at time r. We can alternatively write this as the statement that for all bounded measurable functions on the state space, the transition operator q of rt of f is equal to the composition q of rs times q of st of f. and that's true mu xr almost surely. So this is a nice consistency property for these transition kernels. And it would be nice if we could characterize the Markov property in these terms. But it's a little more subtle than that for two reasons. First, this could be problematic. All we know is that this holds almost surely with respect to the law of the process at time r, the smallest time in the triple r, s, and t. But that law might not be a nice law, and in particular, as we vary r, we might get a sequence of laws that are all mutually singular or something terrible like that. We really would rather not deal with those kind of measure-theoretic problems. So, in order to define a Markov process, we're going to insist that this holds not just almost surely, but literally everywhere. A set of probability kernels indexed by s and t with s less than or equal to t, or equivalently, their set of transition operators, are called Markov transition kernels, or Markov transition operators, if this consistency condition holds everywhere. That is to say, Q of RT is equal to Q of ST followed by Q of RS. That's true for R less than S less than T. We can also make it true at R equals S or S equals T just by making the boneheaded definition that at SS, the transition kernel should just be a point mass at X. That's equivalent to saying that its transition operator is just the identity operator on bounded functions, which is what you have to have if Q of Rs is supposed to be the regular conditional distribution of XS given XR. Since conditioning XS on XS just gives you XS, the regular conditional distribution just has to be the identity operator. These consistency conditions together are called the Chapman-Kolmogorov equations, and they are going to be the bread and butter of how we deal with Markov processes. In fact, that's how we'll define Markov processes. Given a filtered probability space, an adapted stochastic process is called a Markov process if it satisfies the Markov property and there are Markov transition operators that mediate the regular conditional distributions everywhere. Again, the subtlety here is that we can derive the existence of these Markov transition operators as regular conditional distribution operators, but this equation will only hold under the assumption of the Markov property almost surely with respect to the smaller time, s, and we want it to hold uniformly across the entire time set. Now another subtlety is we derived the Chapman-Kolmogorov equations in an almost sure form from the Markov property, and it's natural to ask whether the Chapman-Kolmogorov equations therefore imply the Markov property as well. And the answer to that is no. It is possible, even with a 3-element time set, to construct a process which satisfies the Chapman-Kolmogorov equations but does not satisfy the Markov property if there's enough symmetry around. We'll explore that a little bit later. However, this is pretty subtle because, as we'll see in the next lecture, starting only with the Chapman-Kolmogorov equations, we can always construct a Markov process having the Markov property with those transition kernels. The distinction there is like Skorohod's theorem, which tells us that if we have a sequence of functions that converges in distribution, we can construct a coupling of those laws where the random variables converge almost surely. But that doesn't mean that weak convergence implies almost sure convergence. Before we start exploring those kind of subtle technicalities, let's at least provide some examples of Markov processes. Now, we've actually already seen a couple because of the following. A process is said to have independent increments if its increments are independent. That is, for any sequence of times, t0 less than t1 up to tn, if I take the displacements, xt1 minus xt0, and then xt2 minus xt1, and so on, these random variables should always be independent. We've already seen two examples of these. For example, random walks, where we achieve xn plus 1 by adding something independent to xn. And the Poisson process, we spent an entire lecture showing that in fact it has independent increments in continuous time. Any adapted stochastic process that has independent increments is a Markov process with respect to the filtration that that process generates. And in fact, you can always simply describe the Markov transition kernel Q of S and T at X and a set B, you can compute by calculating the expected value of the indicator of the set B on little x plus the increment xt minus xs. Showing that these are Markov transition kernels, that is, they satisfy the Chapman-Kolmogorov equations, and in fact are the transition kernels of the original independent increment process, is on your homework. Now let's spend a moment focusing on the discrete time case to try to understand the Chapman-Kolmogorov equations a little better. Suppose we have a discrete time Markov process with transition kernels Qmn, with m less than or equal to n being natural numbers. The Chapman-Kolmogorov equations then tell us that Qmn can be recovered by taking Qmm plus 1 times Qm plus 1n. And if we iterate that, we get that this can be recovered as Qmm plus 1 times Qm plus 1 m plus 2, etc. through Qn minus 1 n. So that tells us one thing right away, that in the case of discrete time, it is sufficient to know the one-step transition kernels. If I know each of the one-step transition kernels, then I can compute the transition kernel between any two times. Now, if we also consider the case where the state space is discrete, then these one-step transition kernels we get just by summing up over all of the states the transition functions, Qm plus 1 of x and y for any two states. In this case, as you showed on your homework, this is a regular conditional distribution of xm plus 1 given xm. That is to say, Qm m plus 1 of xy is just the probability that xm plus 1 equals y given that xm equals x. Or we can set this equal to 0 if the probability that xm equals x is 0, in this case, if we want to be careful. Now, this composition statement here from the Chapman-Kolmogorov equations then takes on new meaning, because what it says in terms of these kernels summing up every time is that to compute the transition kernel from time m to time n, going from state x to state y, what we do is we start at state x and then take all possible chains of states going from x to some new state, and then from that state to some other state, and then all the way to some other state getting us to y. And we multiply these matrices, this is just matrix multiplication here, and sum up over all of those states. So this says that in order to get from state x to state y, starting at time m and finishing at time n, the way you compute those transition probabilities is to sum up over all possible chains getting from one to the other all of the conditional probabilities going from one state to the next. That is, in this discrete context, to go from state x to state y, we have to consider all possible paths through the state space that get us from state x to state y, and add up all of the probabilities of going along that path to get from state x to state y. That's what the Chapman-Kolmogorov equations tell us. And in the continuous time analog, this is a version of what you might have heard physicists talk about as path integrals. And in fact, we will come back to that in a future lecture and be precise about what that means. Now remember, the minimal information that we'd like to acquire about a stochastic process is its finite-dimensional distributions. The distribution of xt0, xt1 up to xtn at any fixed finite set of times, t0 through tn. That doesn't tell us everything about the stochastic process, but it's the minimum information that we would like to be able to compute with. For Markov processes, those finite-dimensional distributions are easily described in terms of the transition kernels. And here's how. If I have any sequence of times that will, of course, order in increasing order, and if nu0 is the law of the process at the first time, then the law of the random vector xt0, xt1 up to xtn can be described succinctly as follows in terms of the products of the transition kernels at those times. In other words, and this is equivalent to describing the finite-dimensional distributions, if I want to compute the expected value of a function of xt0 times a function of xt1 times a function of xtn, I can do so by taking the expectation with respect to the starting state, nu0, of f0 times the transition kernel from time 1 to time 2 of f1 times the transition kernel of the process from t1 to t2 of, and so on down the line, of fn minus 1 times the transition operator from tn minus 1 up to tn of fn. Before proving this, let's note that what this tells us is that the starting distribution, together with the transition kernels, which really describe the two-dimensional distributions of the process, determine all of the finite dimensional distributions. That's really what a Markov process is, one where information about any pair of random variables tells us all the information about the finite dimensional distributions of any collection of the random variables in the process. Now we're going to prove this by proving this version of the statement here, because by Dynkin's multiplicative systems theorem, if I know how to integrate a measure against tensor product functions, then I know how to integrate it against all functions. So we're going to prove this formula here holds, and we're going to do so by induction. Now the base case is just the statement that nu0 is the law of x at time 0, which is part of the definition. So we just need to show that if we've proved this formula holds at level n, it also holds at level n plus 1. And to do that, we start by taking the expected value that we're interested in here. By the Tower property, we'll compute that expected value by first conditioning on the sigma field up to time tn. Tn here is the penultimate time, and all of these random variables are measurable with respect to this sigma field. That means, by the product rule for conditional expectation, that inside this overall expectation, the only thing that the conditional expectation is applied to is the last term. Now, because we have a Markov process here, this conditional expectation is the same as conditioning that function of xtn plus 1 on just the random variable xtn, and that, by our definition, is calculated by computing the transition kernel qtn tn plus 1 of the function fn plus 1 and evaluating at xtn. And so what we see is that we've reduced the product inside this expectation to a product of terms only at times t0 through tn. That's how the induction works. To make that precise, notice that we're going to have a function fn times this function of xtn. And so let's call that function gn. That's fn times the transition operator from time tn to tn plus 1 of fn plus 1. And so that says that this expectation is the expected value of f0 at xt0 up through fn minus 1 at xtn minus 1 times gn of xtn, that product of the last two terms. Now, by the inductive hypothesis, we can express this in terms of the formula. We expect the value with respect to the starting measure of f0 times the transition kernel t0 up to t1 of f1 times the transition kernel q at t1 up to t2 of, etc., up to fn minus 1 transition kernel tn minus 1 up to tn of gn. But that gn there, as we just wrote, is fn times the transition kernel from n up to n plus 1 of fn. And so that reproduces this formula at level n plus 1, and we have shown what the finite dimensional distributions of our Markov process are. So we have a fairly elementary description of the finite-dimensional distributions. In the discrete time and discrete state space case, this amounts to matrix multiplication, as we saw. Of course, right now we might be talking into the void because we don't have very many examples of Markov processes to deal with, other than the few that we've constructed explicitly. So our next goal is going to be constructing Markov processes with given transition kernels.